Okay, so hi everyone, and thank you very much for coming. So I'm Rui and Sophie. We're going to talk a bit about collaborative filtering and why you can choose microservices to improve your experience in deploying these kind of intelligent applications and why they make sense. So we're first going to talk about a bit of introducing collaborative filtering. I'm sure many of you are familiar with it. We're going to talk about one of the most popular implementations, which is the alternating least squares. And we'll then briefly talk about what Spark, Apache Spark already provides, and we'll look at why we can choose microservices to deploy these kind of applications. And then finally, we'll look at some problems that we've encountered, some obstacles, and some ways of getting around them, some limitations of these algorithms. So I guess the first question is, what is a recommendation engine? So a recommendation engine, in a way, is a family of algorithms that allow you to define an affinity between a user and a product. And there are a large variety of approaches to this problem. Some are knowledge-based systems, content-based systems, but collaborative filtering is a very popular way of implementing recommendation engines. And we'll focus on a specific implementation of this, which is, as I mentioned, alternating with squares. So how does this work, collaborative filtering? So in the majority of cases, you have a unique mapping between a user and a product, which is given by a rating. And the collaborative aspect of this refers to the fact that you're using a collective pool of information from your users. And the filtering is just simply prediction. So it's just a synonym for prediction. So we use collaborative filtering in our daily lives. And when it's explained the way I'm going to put it, it really seems like common sense. So the main principle is that if a group of people collectively have similar tastes, then it is very likely that you're going to share a similar affinity with a product than that group, right? So let's imagine you have two groups of friends, like group A and group B, and group A has very similar musical tastes to you. And group B is a group of friends which has a very different musical taste than yourself. So if group A recommends you an album and says you have really to listen to this album, and group B recommends you another album, so you really have to listen to this one, so which one are you going to choose? So I guess, as I said, it's common sense, right? You're going to choose what group A is recommending to you, right? So, and just as a bonus question, if group B says an album is really bad, can you make any inference on that? Yeah, no, you can't. I mean, you don't have any affinity with that group, so you really can't make anything of that. So collaborative filtering in this way, if you consider that you have the users and the products, and you can order them in some kind of sequential manner, then you're going to have a unique matrix of ratings, right? So this is going to be your whole representation of the data. And in this representation, each entry represents the rating for a unique combination of user and product. And the matrix will be sparse by definition, because obviously not all users are going to rate all the products, because if they did, you will need a recommendation engine probably. And the way that alternating least squares work is that you factorize this ratings matrix into two matrices which contain the latent factors. And these latent factors, when multiplied back, they're going to give you an approximation to the original ratings matrix that you had. And the output of these two matrices is will approximate the missing ratings that you have, and that's a prediction, right? So if you want to get a prediction for a certain combination of user and products, you just multiply a row from the user latent factors with a column from the product latent factors, and you get back the approximation for that rating, right? So there are several ways to tackle this approximation, and you can do it in streaming, you can do it in batch, but we decided for this use case to show microservices, we're going to use an off-the-shelf solution. So we're going to use Spark's implementation of this from MLlib, and that's a block batch alternating least squares implementation, right? So the block batch factorization actually works by fixing one of these latent factor matrices and solving in order of the other one. Then you just alternate which one is fixed until you reach a certain convergence criteria, and then you have your latent factor approximation. So once you have these latent factors, you can use them, as I said, to multiply them back and get the whole ratings approximation, right? And these will be your predictions. So the question is, why should you use microservices to do this? So when designing a system like this, there were a few core capabilities we wanted to put in our use case. So we wanted to be able to retain the ratings information, right? So we wanted to save them and be able to update them with new ratings. We wanted to obviously train models, right? We wanted to also keep historical models. We wanted to keep old models and simultaneously be able to use two models to do a comparison, for instance. And we wanted the system to scale to millions of ratings and users, possibly. So we wanted the latency between predictions to be quite low. And we also wanted the whole engine to provide an API so that people could consume these predictions in a variety of ways. So using microservices, we could separate these concerns quite easily, so they're cross-cutting concerns, and we can implement them as independent services, right? So we can see here the fundamental blocks of each service, which corresponds to a capability. And this architecture is quite appealing, since each individual service can be built individually, right? So if we want to configure individual services independently, you can do it. And if they communicate exclusively via an API, so that keeps an isolation on each service, which is also desirable. And to take full advantage of this, we wanted to containerize these microservices and possibly use them in a distributed manner. So we decided to use OpenShift as our deployment platform to do this. So nowadays, if you have a big team working on a project like this is a use case, but you could do it in production. So you're going to have people with different sets of skills working on this, right? So you're going to have an heterogeneous team, and you're going to have software engineers, you're going to have data scientists, you're going to have data engineers. And in this scenario, the microservice architecture has another advantage. So if you divide a monolithic app this way, you can have specialized services, and then each person could contribute to a service according to its area of expertise. So for instance, data scientists could focus on the machine learning components, like the modeler and the predictor, and then you can have software engineers working on the data store, working on other backend problems. You can have people doing web design for a front end, for the user-facing components, etc. So this also allows to swap out any service with minimal disruption, right? So you can actually replace them, replace implementations, refactor them. That makes it quite easy, this type of architecture. And operational tasks get simplified as well, because you can implement monitoring or performance or monitoring or benchmarks on each service independently, which is quite easy to do with each service independently. So this allows also to have like polyglot implementations, which is very useful. So many people in data science prefer to use Python, other people prefer to use Scala. So, but it wouldn't matter with this kind of architecture, because you would work on each service independently. So the data scientist in this case could work on a model and predictor components in Python, right? And the functionality being split, it's basically in three broad areas. So in this case, you have the machine learning components, the model and the predictor. You have the storage, which corresponds to the data store and the cache store, and you have the user-facing components, so the front end. So the data store is, in our use case, is a Postgres database where the data resides. We have a model store, which we chose MongoDB, but the backend is agnostic, so we could just swap it out with any kind of other database for the model store. And we have the cache store, which is responsible for caching the recommended predictions. And in this case, we chose InfiniSpan. And the machine learning specific services, which I mentioned, are the model and the predictor. The model is responsible for ingesting data from the data store, train a Spark ALS model, and store it on a model store. And the predictor consists of a REST server, which consumes the model from the model store and utilizes them to make predictions, right? And we have the user-facing component, as well, the front end, which will consume the prediction endpoints, REST endpoints from the predictor, and also will consult the data store to get additional data it might need, like real product names, user profiles, etc. And the modeler and the predictor are the only components or the only services in this implementation that actually have access to a Spark cluster. So, as I mentioned, we're going to use Spark ALS. And now Sophie will talk a little bit about one of the first components, which is the modeler.
Thanks, Rory. So just out of interest, who here has used Spark before? Okay, cool. So if you haven't come across it before, Apache Spark is, in its own words, a fast and general engine for large-scale data processing. So you can use Spark interactively from the R, Python, and Scala shells. The code I'm going to show here is in Python, but hopefully you can see that we don't need many amendments to get it running in a different shell. Let's have a look at the services which specifically use Spark. That is the modeler and the predictor. So within Spark, we've got this PySpark MLlib recommendation package and module, and within that we've got an ALS class, and that meets all of our approximating least squares needs. So as Rui said, the modeler is the service which takes that ratings matrix R and decomposes it into two factor matrices U and P, such that the matrix product of U and P is approximately equal to R when we multiply them back together. In Spark, there's this function called train, which lives within the ALS class, and it takes in a ratings matrix in the form of a RDD, a resilient distributed data set, along with some parameter values, and returns those two matrices U and P. So for the remainder of this talk, when we talk about the model, what we're really thinking about is those two matrices. So the three parameters of the model are rank, lambda, and iterations. So let's take a little look at those. So rank is simply the number of features that we have in our approximating matrices U and P. So in this example, U has k columns, P has k rows. Our rank is k. In order to get these matrices U and P the way that alternating least squares works is that first we fix U, we optimize for P, and then we fix P and optimize for U, and we repeat this process. The more time you repeat, the more accurate the results are. And iterations is the parameter that controls how many times we do that. And finally, lambda. So when we are fitting a model to training data, you don't want the model that you build to be too reliant on the training data. So we saw an example earlier where image recognition model was trained using pictures of wolves with snow in the background, and then it thought that when it saw snow, it must be a wolf. And we'd like that not to happen. So in a similar vein here, we've got some data points given by the circles, and the true model we'd like to fit is that blue line. But if we're not careful, we'll interpolate those points and return the red line. So lambda is a regularization parameter, which prevents the overfitting. So later I'll talk about how to select the parameters initially, and I think Rui's going to give us some insight into how we keep them updated. But for now, let's talk about the other microservice which is running on Spark, and that is the predictor. So once we've used that ALS train function that we saw earlier to build as a model, we need to be able to make predictions. And luckily in that ALS class, we've got this predict all function. It takes in an RDD of user product pairs and returns the prediction. Great, what more do we want? Well, not much, so let's have a little look at an example on a real data set. So the dataset we're using is the Movie Lens dataset, and it was collected by the Group Lens project at the University of Minnesota. As the name suggests, this is a dataset which contains information about films, so users have rated films. There's a few datasets in there, so there's a small one with 100,000 ratings, and that's really useful for initial diagnostics and training. And then there's a full data set with 26 million ratings, and that's good for building a more robust model. So within those data sets, there's a few files, but the one we're most interested in is this ratings file. So it contains a user ID, a movie ID, a rating, which is a value from 0.5 to 5 on increments of 0.5, and a timestamp. So to begin with, I'm just going to rate some films. I've rated all of the classics. So what we see there is the film ID and then the rating that I have given those films. So they're stored in a Python list in that first box. And the first thing I do in box number 2 is turn them into an RDD. I also add my user ID, which is that 138,493. So that's just a value that was not yet taken in the matrix. In the next line, I go on and append my ratings to the main ratings matrix. And then finally, we build the model. So building the model with 10 iterations on that large data set takes about 2 minutes, and on the small data set with 100,000 takes about 10 seconds. So now that we've used the train function to build the model, we need to get some predictions. So I decided I just want to know what my prediction is for the first 10 films in the list of films. So in this first line, I make an RDD which contains my user ID and the film IDs. The second line, we're using that predict all function that we saw to make the predictions, and then I do a little bit of Spark manipulation to make the output more interpretable. So what we're seeing here is the film ID, the rating predicted for myself, and the film name. So hopefully from here it's apparent that we could go on to return, for example, the top K films that one would recommend to a user, or give a specific rating for a specific film and a specific user. So we talked a bit about the parameters and what they are, but how do we choose them? Well, we're using a standard training and validation method. So we take our initial ratings matrix R and we split it into 2 sets randomly. 60% we use to train the model, and the remaining 40 is used for validation. So what we do is we fix some parameter values, we build a model on the training data, and then we evaluate how good it is on that validation set. So for every user film pair in the validation set, you make a prediction, you compare it to the prediction that the user actually gave for that film. And we're using a metric of mean squared error, but you could use whatever your favorite metric is. So here we see a plot for root mean squared error and rank, and the same for lambda. So we pick a rank of 9 and a lambda of 0.07, for example. Now, iterations, on the other hand, isn't quite so straightforward. So root mean squared error is monotonically non-increasing in iterations. So what that means is, as we run more iterations, we're never going to see a worse prediction. It's only that we're never going to see a worse root mean squared error. It's only ever going to get better. However, it's completely unrealistic for us to say, let's do 10,000 iterations, because we'd be sat around for weeks, months, years. We want this to actually function. So we've got to strike some balance there between root mean squared error and time taken. So we're just using a basic rule of thumb, which is that if the root mean squared error at iteration t is less than 1,000th of the root mean squared error at iteration t minus 1, the previous iteration, then we stop. Okay, so you might have noticed that we've selected all of these parameters independently. So in preliminary work, we were looking for the joint set of parameters that minimize the root mean squared error. But we quickly found that the parameters were uncorrelated. So this is really disappointing from a mathematical standpoint, because it'd be really cool if there was some complex underlying relationship between the parameters. But from a computational standpoint, we're happy because it eases the computational cost on our training. So I'm going to pass back to Rui, who's going to talk about the other microservices in the system.
Okay, thank you, Sophie. So those are the 2 machine learning components of the recommendation engine implemented with microservices. And we'll look now at some of the other components separately and how we went about putting them all together. So we can start by the data store. And the data store consists, as I mentioned, as a Postgres database to store the ratings data. But this data will be accessed by the modeler and model training, and also by the front end to display additional data like user profiles also mentioned. This is backend agnostic, so as you write an API for the data store, and this allows you to easily swap data stores within this architecture, so you don't need to touch any of the other code, since all of these services are communicating via a common API. The main role of the data store then is to keep persistent ALS models. So this can be queried either specifically by a certain model ID, so if you want just to reach for a certain model and test it, or if in production, say you want to use the latest model that's been trained, you can ask for the latest version of the model. This is also useful for A/B testing kind of scenarios, because that way you can spawn two separate services, each one using a different version of the model, say, and you can serve them to different users if you want. The other model, the other service, which Sophie mentioned as well, is a predictor service. So this consists of a REST web server. In this case, it was implemented as a Python Flask application, and it's responsible for providing the predictions based on the retrieved AOS model. So the two main types of results supported are an ad hoc user product prediction. So you just supply a list of users and products, and you get the ratings, the predicted ratings for that combination. Or you can get like a top K prediction of the top K highest rated products for a certain user. And the predictor connects to the model store to fetch the ALS models and stores the predictions in the cache store if they're not present already in the cache store. So the predictor checks for new models periodically, but this is configurable because, say, if you don't want to waste computational resources because you're going to have lots of data passing around, you can restrict the model checking to a certain interval, like, say, 5 minutes, if you're sure that you're not going to have a new model in more recently than 5 minutes. So this can help you not throttling the whole service. But this is configurable in real time, so if you want to change the pooling period, you can just change it and nothing else will change on your implementation. So the model returned from the model store is returned as a collection of latent factors. So the latent factors we saw relating to the ALS result. And so this is a collection of feature vectors along with some metadata. So this raw data needs to be instantiated into ALS, into a Spark ALS model. And this is one example of one of the obstacles that you might find with this implementation. So the Spark ALS representation consists of a specific instance of a class in Spark, which is a matrix factorization model class. And this not only is not exposed in PySpark's API, but also the parameters you need or the data you need to initialize are typed with Scala types, so not even Java types, which you can't easily do from Python. So what can you do? So a possible solution, which is the one we implemented, is to write a thin layer, a Scala jar, that's responsible for the type conversion. So you just read the data from the model, you pass it to this thin layer, and then you get the instantiation of this model, and then you return it back to your PySpark driver. So when doing this, you need to know a little bit about how Py4j works and how this data moving around is going to be instantiated, because it can make a huge difference. So, for instance, in this specific case, we had two options. We could either convert the data to an RDD from the Python side and then pass the instantiated RDD to the thin layer for type conversion, or we could just pass the whole data to the thin layer and then do the conversion, the type conversion there, and then convert it to an RDD. And this makes a huge difference in terms of performance. So just as an example, we had a 200-time difference in performance. So if you pass the data first and instantiate it after, it took around 3 minutes. And if you instantiate first the RDD, then you're just losing 1 second, even for a very big amount of data as the big ratings data set. So this can make a huge difference. So I think one takeaway message is to be aware of what Py4j is doing, because, well, it's not always very intuitive what Py4j is working. So the predictor service, also being a REST service, implements the following endpoints. So we ask for a prediction by issuing a post request, which creates a resource for that specific prediction, and it returns a unique prediction ID, right? And if the prediction is not cached, then we store it in the cache store. And if it is cached, then we're just going to reuse that value when we need to return that prediction. We return then the prediction using a GET request and a unique ID. Right? And the cache store is also synchronized with the model lifecycle, so that when we have a new model retrained, the whole cache is invalidated, so we never have to worry about stale predictions. Sorry, I'll just skip this. So I also mentioned A/B testing, and that's quite useful with this kind of architecture. So for instance, let's assume you wanted to implement a custom prediction algorithm, right? But with the Spark off-the-shelf ALS. So we wanted to use, say, some post-processing on the data that we have. So in this case, in a microservice architecture, we simply instantiate a new service. So we instantiate a new predictor. And we implement the code changes that we need in that new predictor service, and then we can provide users with different predictions based on some kind of balancing. So we could provide this functionality in production, so that would be quite easy to do in an environment where these services are containerized, and we provide a certain model or a certain predictor according to our specification. So we've chosen to deploy this on OpenShift, as I've also mentioned previously. And well, we did this because it's a simple way of deploying containerized services. So we need a different number of components, all these ones that we mentioned. And in this example, for a model store, we just need a Mongo database. So this can be easily deployed from a service catalog in OpenShift or by using these commands in the command line. So in this case, we just deploy a pod using a Mongo database and specifying some credentials and a base image. And that's pretty much it to create a data store. So to deploy the predictor, in this case, we use the Python STY on OpenShift. So we point to the source code location of the service, right? So this will create a container and deploy the pod automatically based on your source code. And you can see that we can set up the service plumbing by passing environment variables. So it's quite simple. So in this case, we just specify the location of the type conversion layer, in our case, the location of the model store. So that'll be the other pod running MongoDB, our entry point, which will be whatever you decide it to be, and an application name. And we have the predictor running. So Oshinko is a part of a community project called Rad Analytics, and it's an essential part of this implementation. So basically, what Oshinko allows you to do is create Spark clusters within OpenShift. So in that way, you just, as you see, create a resource for Oshinko, and then you can just create Spark clusters by name, and then just pass the value of Spark cluster as an environment variable to your services, and the plumbing is done. And you can just use the Spark cluster on your OpenShift deployment. So I guess some takeaways from the experience of implementing a use case of an intelligent application using microservices is that, well, Spark is quite well suited for this kind of off-the-shelf implementations. MLlib provides you with the basis of what you need to get started, and it also allows you to deepen some algorithms or change them if you want. By splitting the app into microservices, you also have the freedom of replace the components that you don't like. So let's say that you don't want to use Spark's ALS. Well, that's fine. You can implement your own Spark recommendation engine and then just replace the microservices that you do the prediction and the modeling, and then all the rest will be untouched. You don't need to change them. This architecture also makes it quite easy to change use case if you want within a certain context. So if you think about our architecture, the only thing that's actually tied to the data is the source that you use and the front end. So if you don't want to use movie recommendations, if you want to do book recommendations, the only thing you need to change is the source data and change a little bit on the front end. All the rest will be data agnostic, so you don't need to change a line on your code. And this is quite well suited to deploy on containers. So if you want to get started with microservice deployment of these kinds of services, you can check out the GitHub repo. So everything is there that you need to get started. Just download it, run a few simple commands like the ones I ran for the MongoDB and the predictor, and you can play around with them. So that is all from us. Thank you very much for your time and attention. And if you have any questions, we'll take them.
Thank you very much, Rui and Sophie. Any questions, guys? I cannot see the other. Okay, yeah.
So I have two questions. First would be why you decided to use MongoDB and not just store, I don't know, some blob with the model to not have a problem with this data types? And the second question is, do you know maybe any tools to manage the deployment of models? So basically to have some simple way to decide that this predictor works on this model and manage this easily.
Right. So regarding the first question, it really doesn't have to be MongoDB, obviously. And I think one of the points of choosing MongoDB is to showcase that you can actually replace MongoDB with something else. And as long as the services communicate via a common API, you don't need to change anything else on your code. So that's a very good point. But regarding the type conversion, the problem is that if you have a containerized and isolated data store, you're just going to get arrays of numbers, say. So you're going to have to instantiate them into Spark anyway. So you're going to hit that problem. So if you try to do the whole thing in just one service, then you start getting into the monolithic way of deploying things, and that's the opposite way of the microservices. Regarding tools to monitor model performance, that's another advantage. Well, in answer to your question, no, I mean, I'm not aware of any way of monitoring specifically the performance of this apart from probably the common ways of doing it, like you can test it against a validation set, or I'm supposing you're talking about the prediction performance.
So basically what I mean is I have like one predictor
Mm-hmm.
one model and other model, and then I decide that I want to this week that some model is ready to go into production, or that I don't want this second model anymore, but I want to run predictor from that model.
Mm-hmm. Right. Okay. So in that case, so the question is, if you're using more than one model, say doing A/B testing, and then at some point you decide, well, in production I just want to use model 1 instead of using model 2. How do you do it? Well, that's one of the advantages of using the platform that we chose, OpenShift, because in this case, for instance, if you have a certain model deployed via environmental variables, if you change those variables, it will actually redeploy the whole service automatically for you. So you can actually control it almost in real time what you want to do. So it's quite easy to make those adjustments with minimal disruption to your code, right? So all the other services will be working as normal, and you can just quickly shut down one predictor and then route all the traffic to the other one. So that's quite simple to do, actually.
As a data scientist, that blew my mind. So you can sort of go into the interface on OpenShift. To me, running something on a cloud was quite scary at first, but you can see it, and then you can see all your environment variables, and you can literally change it. If you had rank 5, I say rank 6. I see the pod for the modeler, the microservice. I see it go down. Says, okay, we've cancelled that one. And then it shoots up another one with the new environmental variables. It's pretty cool.
Thank you for your question.
Cool. Correct me if I'm wrong, but it sounded like you have the batch mode training. So essentially you train the models and then you use them. Recommendation engines like this would probably be very useful if they learn along the way, right? So the more data the actual user choices they have. So have you thought about this and how you'd implement it in this way?
Yes, I have actually an implementation for that, which you can, I guess, sorry, I should have put the link there. So I have a blog post about that, doing streaming recommendation engines. So in that case, instead of doing the whole batch thing, what you do is, because if you remember, you have those two big latent matrices, which can get really big for millions of users and products. So what you do is, instead of alternating between those two, doing all that linear algebra heavy computational operations, you just use stochastic gradient descent to update the gradients for each individual row of the latent factors. So in the extreme case, if you have seen on Spark streaming, let's say you have a mini batch in the extreme case of just one new observation, then you just update the row of one latent factor and the column of the other latent factor, right? So that's quite efficient, and you can do it in a streaming fashion. And actually, on the tests that we did, you do get a very good convergence of the streaming results and the batch results. So when the streaming result processed almost as much data as the batch result, the root mean square is almost the same for the validation set.
Excellent, cool.
Any other questions? Okay, I have one question. You showed the latency. What is the tolerance there when you're having this kind of streaming? Yeah.
Well, we're quite surprised that Spark, if you don't use a cache layer, so if you just do a prediction every time one is requested, it's actually quite good, the latency. So I'm talking about something like less than 1 second. So that's suitable for a small system if you want to just a showcase. Probably not in production if you have like millions of users, but you know it's not impossible to use it without a cache layer. But with a cache layer, you can really have a service that scales. So you can have high concurrency of asking for predictions, and especially because most people will probably ask for something like a top K. I'm not sure. So that will depend obviously on the use case, right? But the prediction will be quick from the Spark side, and with a cache layer, then you can really protect from an escalation of requests.
Okay, good to hear. So, all right, thank you very much once.